Hello everyone, my name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do drought monitoring in the Google Earth Engine platform and MODIS data. We aim to estimate VCI, TCI, and VHI indices that are some of the most common typical indices we use in remote sensing to do drought analysis. But first thing that should be considered in this tutorial is that the study area should be contained with vegetation cover, because the VCI, TCI, and VHI, or VHI means Vegetation Health Index, it's working based on the vegetation condition and changes over the time period. So accordingly, I pick a location in the northwest of Iran. So here included lots of vegetation covers, mostly croplands. So your study area should be cropland or forest or very strong rangeland or something like that, because we want to use NDVI and TCI and also VHI, or Vegetation Health Index. So after set your location, in the first step, map.center-object, focus the programming on your study area. The study area already entitled that geometry here, and now we need two variables to call MODIS NDVI images, NDVI daily images, or 8 days NDVI. It doesn't matter because we want to convert them to the monthly formats. Accordingly, I make a new variable NDVI equals to, through the search places and dataset, we can find MODIS NDVI images, or you should write MODIS vegetation cover or something like that. In the panel, you can see that many NDVI products are available with different spatial resolution. Because of 1 kilometer spatial resolution for temperature data, it should be better to use the same spatial resolution for the NDVI too. For example, here, vegetation cover every 16 days available with 1 kilometer spatial resolution already corrected and imported into the code as image collection. And then by the filter date, we can define the start and end time here. Make two new variable, time start equals to 2001, because the MODIS data from Terra satellite available from 2001, and end time should be, for example, 2024. We need to call all of the MODIS images for vegetation cover with 16 days temporal frequency from 2001 to 2024, and also then assign the time start and time end. Time start and time end. This should be time end. Yes. To the image collection, and then we need to select NDVI bands. If you go to the data description and bands, you can see that here we have a band entitled NDVI with a scale factor of with one scale factor that should be applied on each MODIS NDVI images to convert the MODIS NDVI ranges to the correct values between -1 to +1 actually. So now just I call or select NDVI images from each image collection in this period, and then I make a new variable to be sure that all of the MODIS NDVI product it's 16 days are available. Run your code, and here you can see that more than 500 MODIS image collections are available here. And then do the same process and also do the same code for the MODIS LSD data. I make a new variable, temperature equals to, through the search places and dataset, write MODIS temperature to show different kinds of temperature products that are available. The products are daily and also 8 days products, because due to the multi-temporal analysis that I'm gonna to do in this tutorial to convert the data from the multi-days to monthly formats, it should be better to use temporal composite data such as 8 days or 16 days instead of the daily images, because the daily images included lots of errors and noises because of the cloud cover and also the sensor noises or something like that. It would be better to temporal composite bands to provide image to use some images with the less noise and also with the less cloud cover actually. So terra land surface temperature with 8 days temporal frequency imported into the code as image collection number 2. Image collection number 2 is here. Because we want to have focus on the code, I change the view here just like that to have main focus on the code, and then by select you need to find the desired bands you need. As you can see in the band descriptions for temperature data, we have a band LST day 1 kilometer and with the escape factor 0.02 that should be applied on each temperature images. But in the next step I will show you how we can do that. Then again filter date with time start and time end. We narrow down MODIS collection data to the specific period and also specific bands. Print temperature data. And here, if we print the temperature data, there is a syntax error. Yeah, by the parentheses, the error will be solved. More than 1000 elements are available. So if we open it up, you can see that one LSD daily with 1 kilometer spatial resolution is available for each date. Here we have two kind of image collections. One of them is 8 days and another one is one of them is 8 days and also another one is 16 days. And also before doing multi-temporal composition and converting data to the monthly format, we can estimate the minimum and maximum values from the NDVI and temperature, because for the first step I'm gonna estimate VCI indices. VCI means vegetation condition index. The vegetation condition index showing the amount of moisture available in the vegetation cover here. So to estimate the vegetation condition index based on time series analysis, we need to have NDVI for each date and also the NDVI minimum values over the time period and also the NDVI maximum values. And finally, the equation should be just like that. VCI equals to, and here, the difference between NDVI of each date and NDVI mean over to NDVI max minus or subtraction between NDVI max and NDVI mean. Max minus NDVI mean, just like that. Yes, this is the final equation for VCI, and we need to calculate it from the NDVI images in the first step. So make a new variable as NDVI mean equals to NDVI.means. It's very simple. .mean is a function that calculates the minimum value of NDVI over the time period from 2001 to 2024. Finally, we will have an image in each pixel, the minimum value of NDVI over the time period showing. So, and the next we need a variable NDVI max, NDVI.max. You can see this. Yes, NDVI max is against the NDVI mean, the maximum value of NDVI over the time period calculated and stored in a single images. So in the next step, we want to estimate the VCI, but as I'm going to do the time series analysis with monthly data, I need a function or temporal collection function that already showed you how it works in my YouTube channel. We need that function to estimate the monthly average of NDVI and temperature to estimate the monthly VCI and TCI and VHI. So here is temporal function. Temporal function is gonna be used to convert data into monthly format. So I make a new function, and this function should has a name. Its name is temporal collection. I already mentioned that the temporal collection or the temporal composite I'm showing you in this tutorial is not my own. It is already developed by the Google developers. Just here I'm gonna show you how it works, and also if you search on the net, it's available and developed by the Google developers, and also I'm not the owner of this function actually. So here you can see that the temporal functions, including some of the arguments helping us to estimate the multi-temporal data. The first one is the collection of the images that we're going to use in this code, and a start time of data processing that should be same as time start here. And the next is the count. It refers to the number of images we want to have at the end, and finally after the count we have the interval, the difference, the temporal difference between sequence of images, and also finally we will have a unit based on which kind of unit we want to get the data, monthly, daily, yearly, or something like that. So first we need to make a sequence list, actually Earth engine.list to sequence, and also this list is starting from 0 to the number that we already set for the count, and because it's starting from the 0 should be subtracted from 1, just like that. And the next is origin date. Origin date equals to ee.date start. One of the arguments is a start, showing the time start, but the time start should be a string and also converted to the date format by Earth engine.date function, as you can see here, start. And now the sequence should be returned as an image collection. Image collection, yes. And here we have a list of sequence as an image collection. For each row of this list we need to do same processing, just like that. By function, by map, I make a new function. Each row in this list consider it as an I, and for each row we need to set a start date and end date. A start date equals to from origin date.advance. There are some arguments. The first is the delta, the temporal difference of input images for each row. Earth engine.number. The delta should be interval, and then apply it to each row of the list based on the unit we want to use. That keep the unit here and make it another variable for the end date, writing like origin.date.advance Earth engine.number. It is same as the start date with a little change. Interval dot multiply here Earth engine.number, number of I should be added to 1. So, and at the end we have units. Based on the unit this calculation should be done. And the next, finally, we will have input collection in a specific period already defined by the start date and end date, just like that, and get its average for from the start date to the end date. And finally, to do the time series analysis in the next step, we need to set the system time start and system time end as the new properties. System time start equals to, so start dates dot millisecond. All of the dates calculations or all of the dates information should be stored based on the millisecond units, because that's how Google Earth Engine works for the time series analysis. That sets system time end, end date dot millisecond. So now I remove some gaps between the code lines. So because we have a function, no need to have semicolon at the end. So a little coming down, and also now we want to make monthly NDVI here. Monthly NDVI image collection. Here I show something to hint you what I'm gonna doing in each step. Make a new variable, monthly or NDVI monthly, better. NDVI monthly equals to temporal function or temporal collection. Temporal collection function. So here, as you see, 5 arguments is available. Instead of collection, I use NDVI instead of the start, time start, and count refers to the number of images we need at the end. So according to the temporal extent, the data should be considered from the data should be called the input data coming from 2001 to 2024. And here for 23 years, we need to call MODIS images each year, including 12 months. Here we have a simple calculations. By the calculator, I can show you for 23 years and each year 12 months. Finally, we expect to have 276 images, 276 monthly images with 1 month interval. Instead of interval, I use 1, and also here as for the unit we use month. So then I print NDVI monthly, and then so you can see that the collection is not defined here. We have a problem. Maybe there is something wrong between the collection in the arguments and also in the code body. I hope it's been solved. Yes, finally we will have 276 elements here, and also we need to have 1 band for each date. If some dates missed some band or some information, you should consider it and also try to solve it through your calculation process actually. So again, now I'm gonna estimate VCI indices here in the new line, vegetation condition indices, or VCI. Here we can estimate it. I make a new variable, VCI equals to, so NDVI monthly dot map. In a function, I will call each NDVI monthly data, and then based on the equation, get the subtract of each date from the minimum. Here we have NDVI mean over to the difference between maximum and minimum that is already calculated. So NDVI monthly dot map. Here we have a function. Each input image is considered as an IMG, and here we have an index. So the IMG dot expression. By the expression, I can write my own function or formula here, and we have 2 parts here. In the first part, we need to get the difference between NDVI images and the minimum value based on the equation, minus mean, and maximum minus mean, like this. And so here, instead of the NDVI, we have IMG.select the NDVI. You can see that here, the NDVI monthly entitled as NDVI bands. So, and after the NDVI, we have minimum values. The minimum values will be assigned to the NDVI mean already calculated in this code, and maximum equals to NDVI max, like this, and dot and code return the index with a new band name. Its name is VCI. To be able to do time series analysis for the next step, we need to copy properties from input img. So then I will print the result VCI here. You can see that 276 VCI should be available here for each date separately. In the next step, we want to estimate the TCI or thermal condition index. For the TCI, I make a new part in my code. TCI means, probably most of you know that what the TCI is, but just in case, I'm showing and also talking about the TCI to have some minimum information about what I'm gonna do in this tutorial. You can get more information through the articles and papers available on the net and different journals and papers, because it's very, very common and typical indices in the remote sensing drought analysis. So TCI means thermal condition index, and also to estimate the TCI or thermal condition index, we need to have LST max and also the LST mean. To get the LST max and LST means, to estimate the final equations to estimate the TCI, like this, we have numerator and denominator here, and also first expression is maximum LST over the time period minus the LST for each date, and maximum minus minimum, or the difference between maximum and minimum of LST should be calculated for the second expression here. So first we need LST mean and LST or temperature mean or temperature max. Temperature max equals to already we should calculate the we should have the temperature data for the time period, as we already made it by the temperature function, temperature variable, and here the temperature dot maximum estimate the maximum value of land surface temperature for each pixels over the time period already selected from the 2001 to 2024. And next we have temperature mean equals to temp dot mean. The mean is a function against maximum, as I told you before, estimates the minimum value of LSD per each pixels over the time period already selected. So now we need to convert the 8 days temperature data to the monthly format, same as NDVI. You can copy NDVI monthly just like that and paste it with some minor changes. Instead of NDVI temperature monthly, same function, leave it as same, and instead of NDVI, import the temperature data with the same number of the months, with the same interval, with the same unit of time actually. So finally we expect to have 276 monthly LST images. That is the average of LST per month or for each month. So temperature monthly, you can see we have 276 image collection, but I missed something here. We had an scale factor in our computations. After NDVI monthly calculated, we need to apply the scale factor of NDVI for each input images here. We can do it here, or even we can apply it in the expressions for the VCI. After selecting NDVI, you can apply the scale factor for NDVI. We already talked about that in the bands. You can see that here we have an scale factor that should be applied by the multiply function on each input NDVI values. And also don't forget this, because it's very important to convert the NDVI images from the primary range to the main range between the -1 to the +1. It's very important. And also the same thing should be done also for the LSD data. So for the temperature monthly, you can see that the monthly temperature is available, entitled LSD day 1 kilometer for each band. And then we need a new index, we need a new function to estimate the thermal condition index for each date. A new variable TCI equals to temporal temperature monthly, or monthly temperature, dot map into a loop. We need a function considered each input images as an IMG, and then estimate the desired index, that is TCI for here. So IMG.expression, the main expression for the TCI already showed you, maximum LSD minus LSD for each date, the maximum LSD minus the minimum LSD. So here the maximum LSD already defined as NDVI max, the minimum LSD already defined as temp min. Here you can see them. And also each input LSD images, or each LSD in each date, coming from IMG dot multiply. IMG is LSD monthly LSD. By the multiply, we can apply the scale factor of the LSD that I already showed you. So here we have a TCI. The function return desired index or calculated index with a new band name as TCI, and like this. And finally, we need to copy properties. Copy properties of input images. Most important one is system time start and system time end to do the further analysis. So after this part, we need to combine the TCI data and also the VCI data in a same image collection. So to do this, we will have a new variable. It is, for example, MODIS indices equals to VCI.combine. Combine is a function that collects VCI and TCI for the same dates into a single image collection, actually. VCI and TCI. Here, if you print MODIS indices, then for each date you will have one TCI and one VCI. Here we have an image collection, two bands VCI and TCI, and using VCI and TCI now we can estimate vegetation health index, or VHI. So in the next part we wanna have a VHI equals to vegetation health index. The vegetation health index showing the vegetation health condition, in higher values showing higher health condition, lower value lower healthy, or something like that. To estimate vegetation health index, the equation is like that: VCI equals to alpha, typically considered as 0.5, multiply to the VCI plus 1 minus 0.5. Typically alpha is 0.5, as I mentioned, multiply to the TCI. So we have VCI and TCI, and typically alpha considered as 0.5. Now we can estimate vegetation health index for each date. So make a new variable. So it is drought because we're gonna have VCI, TCI, and VHI together in a single collection. Drought equals to get MODIS indices dot map, throw a loop and a function for each input image as an IMG. We wanna have VHI index. VHI equals to IMG. The IMG included VCI and TCI. That expression, the expression is like that. Alpha 0.5 multiply to VCI index plus 1 minus the alpha value 0.5 here multiply TCI. So then, but here should be VCI. Yes, VCI equals to from input image select VCI for this. From input image select the TCI. From input image dot select the TCI bands, and the rest of them is value and also leave it same and dot rename. Finally we will have vegetation health index or VHI. So the function return the IMG means TCI and VCI with by add bands we can add VHI bands here. Dot copy properties to copy the time series information or the temporal information. So print drought. In each date now we will have TCI and VCI. In here TCI should be capital to solve the problem. We have 276 image for each date. TCI, VCI, and VHI is available. So to plot the trends of variations of the VCI, TCI, and VHI, just you should use some simple functions such as user interface chart image.series, just like that. Print the final result user interface chart image.series. Instead of collection we have droughts, and instead of region geometry, instead of reducer Earth engine.reducer. For the region of a study I want to get the average of VCI, TCI, and VHI. Instead of a scale a spatial resolution. Instead of X property system time start. System time start. Just like that. Save your code and finally run to see the final result. We are waiting for generating chart to see that how VCI, TCI, and VHI changing in our study area. This code is very useful for the drought analysis, and also by the change of a study area you can use it for everywhere in all around the world. And here you can see that the VCI, TCI, and VHI indices. So although the computation successfully is done, but the problem is here about the range of outputs. We expect to have the outputs between the 0 and 1, but here it is they are far from the region or range of values that we expected. We should go through the code and find the problem. I think one of the main things that caused this kind of problem occurred is about the NDVI mean or minimum or maximum values, because after monthly images calculated, we converted NDVI into the correct range, but NDVI minimum and maximum values already calculated based on the original range they have without any conversion. Accordingly, we need to convert them to the same scale factor and to adjust them into the same range between -1 to +1 actually. So 0.3, 0 and 1, and then do the same process for the temperature max and temperature mean, and finally I expect to have a correct results. So multiply 0.02, just multiply 0.02 again, and then let's see what's happening in the code. So generating chart. I'm waiting to see the final result. I hope it works. Yes, there is. And as you can see, now the ranges are corrected, and we have TCI, VCI, and VHI separately in different plots and also in different colors here. And also, maybe it's a little difficult to show them together to see that how they are changing. You can select one of each you want. So here I print a new chart, and also in the drought that only I select the VHI. We can have a single plot for the VCI, a single plot for the TCI, or we can both of them together. For example, here we can also have VCI and TCI together, and a single plot for only VHI to see how we can interpret the results. Save your code. Charts are generating. So here is TCI and VCI, and you can see that and also when the TCI is high, this is the TCI. When the TCI is high, it means the amount of dryness increased in the vegetation. And during a time when TCI increased or decreased, it means that over the periods, the amount of dryness in the vegetation cover or vegetation cover in this region increasing or decreasing. And also the red plot or the red color here showing vegetation condition index, showing the amount of moisture in the vegetation. For example, when VCI increasing, it means the amount of moisture in the vegetation increased, and also when VCI decreased during time, it means the amount of moisture in the vegetation cover also decreased in this region. And vegetation health index or VHI showing the total condition of vegetation, is it healthy or not. For example, when the vegetation cover is high and chlorophyll is high and everything is fine, we have a high VHI. And also when we don't have vegetation, or vegetation is in an inappropriate situation, VHI decreased. But this kind of variation in the plot for the croplands is very typical, because growing season varies, and also when in the growing season vegetation cover peaks, we can see that VHI increase, and after growing season ends, no vegetation cover in the region typically, or as we expected, VHI also decreased. But over the time, we should see that if VHI increasing or decreasing. Increasing VHI, it means during the time the vegetation health improving, or if it is decreasing, it means the vegetation health is decreasing, and also it's a bad sign for the drought monitoring based on the vegetation cover dryness, and also vegetation cover the wetness actually. There are different also indices for the drought monitoring, not included only VCI or TCI. I will try to learn them how to use this kind of indices for the drought monitoring by the precipitation data, by the runoff data, or something like that in the future. Just follow my YouTube page. I will try to share you more other tutorials about the drought monitoring and different kinds of monitoring that we can do in the Google Earth Engine platform. And also, if you had any questions or problems regarding to this kind of programming, you can share your question in my YouTube page, and also I will check them as soon as possible and respond to you. Thank you for watching us.